Fascinating role chemistry. We're looking at gas laws. In order to do it this time, we're looking at the kinetic theory. And remember, a theory is something we believe we assume to be true. It's not considered a law. The reason why kinetic theory isn't a law is because there's 5 postulates we hold to. Explanation of the movement of electrons. So that's what its purpose is. But the postulates are that gases are composed of many molecules in constant motion. Now that's mostly true, but the colder we get, the less it moves. We can end up with what's called the Einstein-Boson condensate, which means actually it's in more than one places at one time. Another postulate we hold to, the volume of all gases equal to total volume. So we don't have any loss of gases. That's mostly true. Attraction and repulsion between gases is negligible. We do have gravity, and we do have electromagnetic forces, positive and negative forces, but we basically ignore those and we'll have this theory hold true. Collision between molecules is completely elastic, so if they strike into each other at 75 meters a second, they're going to bounce back at exactly 75 meters a second. There is actually some loss, but we're going to ignore that. And the last one, all molecules have the same energy at a given temperature. Mass does affect that, but we're going to, again, hand wave it so that we can get around that. So we use those things to give us something called the speed molecular movement. Now, this value is called effusion, movement of gases. The value here is the effusion, E value, is equal to 1/2 mu squared, where E is the energy of the gas, m is the mass of the gas, and U is the value, the square root of 3RT over mW. And that's what we're going to actually be looking at, is the rate of effusion using that value, U. U is called the root mean squared, the velocity of the molecule. Of course, R is the molar gas constant of 8.314 joules per mole Kelvin. And MW is molecular weight, grams per mole, and of course T is temperature in Kelvin. All right, so let's look at a problem. Determine the rate of effusion of sulfur trioxide at 35.20 degrees Celsius. So we take our equation, root mean squared, U is equal to 3RT over MW. We have 3 times 8.314 joules per mole Kelvin times 308.20 Kelvin. And molecular weight is 80 grams per mole. Since it's sulfur trioxide, we take the square root of that, but our units don't cross out. So I need to add a couple values. A kilogram meter squared per second squared is a joule, and a kilogram, 1,000 grams over a kilogram, so that my joules cross out, my moles cross out, my kelvins cross out, my grams cross out, and we end up with meters squared per second squared, the square root of that. So we take 3 times 8.314 times 308.20 times 1,000, divide by 80 and take the square root. We get an answer of 309.98 meters a second. All right, so let's look at the following. We'll do this in class. Find the rate of effusion of carbon dioxide, STP. Diffusion itself, we've talked about last year. Diffusion, the process moving from a region of high concentration to low concentration. Okay, and we use that using Graham's law, which is R1 over R2, sorry about the extra line there, which is actually U1 over U2, and we take the square root, so that's how we get molecular weight 2 over molecular weight 1. So R1 over R2 is either the square root of molecular weight 2 or molecular 1, or the square root of D2 over D1. So we'll do this one in class here. Remember, if R1 over R2 is greater than 1, it's faster. R1 over R2 is less than 1, it's slower. So we'll do this one in class. Calculate molecular mass of a gas that diffuses at 0.555 times slower than chlorine. Okay, and then we'll do these two as practice. Determine the rate of effusion of fluorine gas at 23.22 degrees Celsius. Calculate the density of gas if it travels at 1.0122 times faster than the gas with a density of 2.0115 grams per liter. That's it. We're done. Take care. Be good.